A complete computer guide. Welcome to KD Production. Today I have come with number system. The first question always asking in number system is why we read number system in computer. The answer of it is computer understands only machine level language, and that is in the form of binary or 0 and 1. All the functions of computer perform only in numbers. So, we must understand number system to know how computer works. I hope you have understood why it is necessary to read number system in computer. Now, we have to define number system. A number system is a way of representing and expressing numbers. It consists of a set of symbols or digits and rules for their manipulation to perform arithmetic operations and convey numerical information. Different number systems are used in mathematics, computer science, and various other fields. There are two types of number system. One is positional number system and other is non-positional number system. Positional number system means that number system which has its own position and weight. By one example we can understand it. Let's suppose that we have 32,596 rupees. If we lost 6 from this money, that is only 6 rupees, which is not so much important for us, that is minimum or low. But if we lost 3 from this money, that means it is 30,000 for us, and it is so much important for us. From above description it is clear that the rightmost bit is always minimum and leftmost bit is always maximum, and each digit has its own position and weight. From above description it is also clear that the rightmost bit is called least significant bit, LSB, and leftmost bit is called most significant bit, MSB. Now, non-positional number system means that number which has not its own position and weight. Example of it is Roman numbers. Now, one most important term in number system is radix. The term radix is synonymous with base in the context of numeral systems. It refers to the number of unique digits used to represent numbers in a positional numeral system. In other words, the radix determines how many distinct symbols or digits are available for expressing numbers in that system. For example, in the decimal numeral system, which is also known as base 10, the radix is 10 because it uses 10 unique digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Each digit's position in a number has a different weight or value based on powers of 10. In summary, the term radix is essentially the same as base and is used to describe the fundamental characteristics of a particular numeral system, indicating how many unique symbols or digits are available for representing numbers in that system. The most common number systems include 1. Decimal number system. This is the most widely used number system and consists of 10 digits, 0 through 9. Each digit's position represents a power of 10, making it a base 10 system. 2. Binary number system. In the binary system, there are only 2 digits, 0 and 1. It is a base 2 system and is commonly used in computer science to represent data and perform binary arithmetic. 3. Octal number system. The octal system uses 8 digits, 0 through 7, and is a base 8 system. It's used in some programming contexts, particularly with older computer systems. 4. Hexadecimal number system. Hexadecimal uses 16 digits, which include the decimal digits 0 to 9 and the additional digits A, B, C, D, E, and F to represent the values 10 to 15. Hexadecimal is a base 16 system and is commonly used in computer programming, especially for representing memory addresses and binary data in a more compact form. Binary to decimal conversion. Converting a binary number to its decimal equivalent is straightforward. You can follow these steps. 1. Start from the right, the least significant bit, of the binary number. 2. Assign a positional value to each bit, starting from to 0 and doubling the exponent as you move from right to left. 3. Multiply each bit by its corresponding positional value. 4. Sum up the products obtained in step 3. Here's an example to illustrate the conversion of a binary number to decimal. Let's say you have the binary number 110101. Starting from the right, times the rightmost bit, 1, is at position to 0, so it contributes 1 asterisk to 0 is equal to 1 to the sum. Times moving to the left, the next bit, 0, is at position to 1, so it contributes 0 asterisk to 1 is equal to 0 to the sum. Times the next bit, 1, is at position to 2, so it contributes 1 asterisk to 2 is equal to 4 to the sum. Times continuing this process for each bit from right to left. Times 0 asterisk to 3 is equal to 0. Times 1 asterisk to 4 is equal to 16. Times 1 asterisk to 5 is equal to 32. Times 0 asterisk to 6 is equal to 0. 5. Summing up all the contributions, 1 plus 0 plus 4 plus 0 plus 16 plus 32 plus 0 equals 53. So, the binary number 110101 is equivalent to the decimal number 53. In general, you can use this method to convert any binary number to its decimal representation by evaluating the value of each bit in its respective position and summing them up. Decimal to binary conversion. Converting a decimal number to binary is done by successively dividing the decimal number by 2 and recording the remainders at each step. Here's a step-by-step process for converting a decimal number to binary. 1. Start with the decimal number you want to convert. 2. Divide the decimal number by 2. 3. Write down the remainder, either 0 or 1. 4. Continue to divide the quotient from the previous step by 2 and write down the remainders at each step until the quotient becomes 0. 5. Read the binary result from the bottom, the first remainder you obtained, to the top, the last remainder you obtained. This is your binary representation. Here's an example to illustrate the conversion of a decimal number to binary. Let's say you want to convert the decimal number 53 to binary. 1. Start with 53. 2. 53 divided by 2 is 26 with a remainder of 1. Write down the remainder, 1. 3. 26 divided by 2 is 13 with a remainder of 0. Write down the remainder, 0. 4. 13 divided by 2 is 6 with a remainder of 1. Write down the remainder, 1. 5. 6 divided by 2 is 3 with a remainder of 0. Write down the remainder, 0. 6. 3 divided by 2 is 1 with a remainder of 1. Write down the remainder, 1. 7. 1 divided by 2 is 0 with a remainder of 1. Write down the remainder, 1. Now, read the binary result from the bottom to the top, 110101. So, the decimal number 53 is equivalent to the binary number 110101. You can use this method to convert any decimal number to its binary representation by recording the remainders at each step of division. Octal to decimal conversion. Converting an octal number to its decimal equivalent is a straightforward process. The octal number system uses a base of 8, and to convert an octal number to decimal, you can follow these steps. 1. Start from the right, the least significant digit, of the octal number. 2. Assign a positional value to each digit, starting with 80 and increasing by 1 for each digit as you move from right to left. 3. Multiply each digit by its corresponding positional value. 4. Sum up the products obtained in step 3. Here's an example to illustrate the conversion of an octal number to decimal. Let's say you have the octal number 345. Starting from the right, times the rightmost digit, 5, is at position 80, so it contributes 5 * 80 is equal to 5 to the sum. Times moving to the left, the next digit, 4, is at position 81, so it contributes 4 * 81 is equal to 32 to the sum. Times the leftmost digit, 3, is at position 82, so it contributes 3 * 82 is equal to 192 to the sum. 5. Summing up all the contributions, 5 plus 32 plus 192 equals 229. So, the octal number 345 is equivalent to the decimal number 229. In general, you can use this method to convert any octal number to its decimal representation by evaluating the value of each digit in its respective position and summing them up. Decimal to octal conversion. Converting a decimal number to its octal equivalent involves dividing the decimal number by 8 and recording the remainders at each step. Here's a step-by-step process for converting a decimal number to octal. 1. Start with the decimal number you want to convert. 2. Divide the decimal number by 8. 3. Write down the remainder, which will be a digit in the octal representation. 4. Continue to divide the quotient from the previous step by 8 and write down the remainders at each step until the quotient becomes 0. 5. Read the octal result from bottom to top. The last remainder you obtained is the first digit. This is your octal representation. Here's an example to illustrate the conversion of a decimal number to octal. Let's say you want to convert the decimal number 229 to octal. 1. Start with 229. 2. 229 divided by 8 is 28 with the remainder of 5. Write down the remainder, 5. 3. 28 divided by 8 is 3 with the remainder of 4. Write down the remainder, 4. 4. 3 divided by 8 is 0 with the remainder of 3. Write down the remainder, 3. Now, read the octal result from the bottom to the top, 345. So, the decimal number 229 is equivalent to the octal number 345. You can use this method to convert any decimal number to its octal representation by recording the remainders at each step of division. Hexadecimal to decimal conversion. To convert a hexadecimal number to its decimal equivalent, you can follow these steps. 1. Start from the right, the least significant digit of the hexadecimal number. 2. Assign a positional value to each digit, starting with 16 and increasing by 1 for each digit as you move from right to left. 3. Multiply each digit by its corresponding positional value. Be sure to convert any hexadecimal letters A, B, C, D, E, F to their decimal equivalents 10, 11, 12, 13, 14, 15. 4. Sum up the products obtained in step 3. Here's an example to illustrate the conversion of a hexadecimal number to decimal. Let's say you have the hexadecimal number 1A3. Starting from the right, times the rightmost digit, 3, is at position 16, so it contributes 3 * 16 is equal to 3 to the sum. Times moving to the left, the next digit, A, which is equivalent to 10 in decimal, is at position 16, so it contributes 10 * 16 is equal to 160 to the sum. Times the leftmost digit, 1, is at position 16, so it contributes 1 * 16 is equal to 256 to the sum. 5. Summing up all the contributions, 3 plus 160 plus 256 equals 419. So, the hexadecimal number 1A3 is equivalent to the decimal number 419. In general, you can use this method to convert any hexadecimal number to its decimal representation by evaluating the value of each digit in its respective position and summing them up. Decimal to hexadecimal conversion. To convert a decimal number to its hexadecimal equivalent, you can use a method similar to the one used for other base conversions, but this time you'll divide the decimal number by 16 and record the remainders at each step. Here's a step-by-step process for converting a decimal number to hexadecimal. 1. Start with the decimal number you want to convert. 2. Divide the decimal number by 16. 3. Write down the remainder, which may be a digit in the hexadecimal representation. 4. Continue to divide the quotient from the previous step by 16 and write down the remainders at each step until the quotient becomes 0. 5. Convert any remainders greater than 9 to their corresponding hexadecimal letters. 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. 6. Read the hexadecimal result from bottom to top. The last remainder you obtained is the least significant digit. This is your hexadecimal representation. Here's an example to illustrate the conversion of a decimal number to hexadecimal. Let's say you want to convert the decimal number 419 to hexadecimal. 1. Start with 419. 2. 419 divided by 16 is 26 with a remainder of 3. Write down the remainder, 3. 3. 26 divided by 16 is 1 with a remainder of 10. Convert 10 to the hexadecimal letter A and write it down. 4. 1 divided by 16 is 0 with a remainder of 1. Write down the remainder, 1. Now, read the hexadecimal result from bottom to top, 1A3. So, the decimal number 419 is equivalent to the hexadecimal number 1A3. You can use this method to convert any decimal number to its hexadecimal representation by recording the remainders at each step of division and converting any remainders greater than 9 to hexadecimal letters. Thank you for watching.